Hey, welcome to the presentation on roboRIO and sensors. I'm Tim Irwin.
My name is MX Zhang. So why do you use sensors? So first, a sensor is defined as a device that detects or measures a physical property and records, indicates, or otherwise responds to it. So at first, a sensor measures probably a physical input or a digital input, and therefore, and there's a program response to that input. So first, why do you use sensors? So first, one very important aspect of using sensors is using them for feedback for positioning robot parts. In 2015, we had an elevator bot, and that robot, once the elevator reached a certain point, would trigger a limit switch sensor that could tell, oh, the elevator is there. And then that would enable programmers to move it further or move it down, depending on its function. Motion control is also very important. We use, for example, for motion control, we use encoders, which can measure how fast the wheels are spinning. And that's a very precise measurement of your robot's speed. And there's also the gyroscope and accelerometer, which measures rotational motion and rotational acceleration and just translational acceleration, respectively. That allows you to know if your robot is turning, if it's speeding up, and it's pretty precise when compared it's pretty precise measurement when compared just like timing-wise. Another aspect we use sensor is just for detecting field elements. If you intake fuel, if you were to intake the ball you have a proximity sensor there to see if there's a ball there, and that way you can sense that there's a ball and get feedback onto your computer, and then you know the ball is there and you can shoot even though you can't see the ball.
So there's several aspects you have to consider when choosing a sensor and like the output that you would like the sensor to give, and to figure out which sensor is compatible. And so you also have to consider the distance, like if you have a proximity sensor, how far away you would need it to sense, the maximum speed and optical conditions. Like for example, in an encoder, some encoders might have a maximum speed, and you would have to know how fast your wheel would be turning, so you would be able to most precisely measure it. And you would also consider voltage and current requirements, so you can supply the needs for the sensor. And price range is also a thing to consider, and some sensors are able to do similar tasks, like a Hall effect sensor and beam brake for proximity, but one might be more expensive than the other. So these are some examples of sensors. So the first one is a limit switch, has Boolean output, which is true or false. And one problem with limit switches is the potential for mechanical failure, because it's a physical switch and it could wear down over time. And this would be used to detecting field elements or internal components in the robot. And a Hall effect sensor is Boolean or analog output, and it detects magnetic fields, and you can also use it as a proximity and limit switch. So that is an encoder. It has Boolean outputs, but it can also do more complex information, and it's used for rotational and wheel speed. And there's also potentiometers, which are variable resistors, and can also be used for rotational position.
For example, one usage of potentiometers is for a turret. When the turret spins, the potentiometer turns with it, and depending on the resistance of the potentiometer, you know how far the turret has turned.
So there's also gyroscopes, which give a serial digital signal, and they're used for angular motion and the rotational position of the whole robot. There's also accelerometers, which are like change in direction and speed, and the roboRIO includes an accelerometer, but 1678 doesn't use that accelerometer because it's not accurate and we don't have a use for it. And there's also proximity and beam brake, which can give Boolean, analog, or serial, and this would be used to detect distance to objects, and it's run with light, and you have to consider what your light would be reflected against, because some materials reflect light differently and might affect the accuracy of the sensor.
Okay, so for Gyros Hookup and accelerometers, you can normally get an add-on for a cheaper price. I know there's a few teams that sell them, such as like 971 designed one for add-on to the at WCT for the roboRIO. Next page. Okay, so how would you implement a sensor? One of the most important aspects of actually using a sensor is mounting it properly. So first of all, the sensor must be protected. It can't like come into the way of robot objects, into fuel, into like gears properly smashing against it. So the sensor must be secured onto an object and move with the object. For example, if you have an encoder, it must be in the shaft tightly. It cannot have any leeway for it to come out while it's running. And the sensor must be able to be easily removed. For example, we've had sensors that such as proximity and encoders break. If you need to replace them, you need to easily be able to replace it without taking apart the entire robot. That's why we also use connectors for sensors instead of soldering, because that way we can disconnect the sensor easily and replace it just as easily. So one obvious fact about sensors is that they must be able to see the target. So for example, if you're using vision, you need both an LED to shoot the light and the camera to take in the light. Both of those must be within line of sight of the reflective tape on the go. Or else you could get interference from the field just piling up in front of the light, and that will often give you mixed signals and not allow your vision to function properly.
So another aspect of implementation is noise. And on a robot, there's many motors which give magnetic fields, and they can interfere with the sensors, especially delicate ones. And so you have to consider where you're positioning the sensor and if it's in a place that will have it interfering, or the magnetic fields interfering with the sensor. And so one way to reduce this effect is with Faraday cages. And is everybody familiar with a Faraday cage?
Okay, so for any of those who weren't familiar, there's a law that if thunder strikes you or there's a metal cage around you, it won't shock you, but it goes through the cage around it. So that's what Faraday's cage is in this sense. So that means the electric field won't interact with you, but won't interact with the sensor protected with the Faraday cage.
So a Faraday cage can be like a metal box or metal mesh, and it would dissipate the energy around it instead of affecting the thing inside of it. So sensors can give out different signal types, like Boolean, analog, and digital. And so the first graph in the diagram is a Boolean signal where it's true or false, so it's either 5 volts or 0. And this type of signal is easy to interpret, but you have a limited use of this because it's only one output. And then the second chart is analog, and it can be a series of voltages in between 0 and 5. And so this can carry more information, but since it's so many values, it can be easily interfered with. And so instead of a smooth curve, it would be a curve with many.
You would just see more like little spikes over it, but you get the general shape of it.
And then the last one is digital, which is a set value between your voltage levels. It's precise, it's less affected by interference, and it gives more information. However, it's more complex to utilize and program.
And so here's just a basic image of the roboRIO. Just the fact that everyone should know is that the pin spacing between the pins on the roboRIO are 0.1 inches. So when you buy housing, make sure that they're for the right size.
So on the upper right corner of the roboRIO, there's a set of lights, indicator lights. And so this is an example of the power LED indicator. And the indicator lights would show the status of the roboRIO, and so there's power, and also an important indicator light is the RSL indicator, which is identical to the robot signal light outside of the roboRIO.
Okay, so how is the robot getting signal? One of the major ways the robot communicates is through CAN. CAN is the wire, the green and yellow wire that goes between the roboRIO, the PDP, and the PCM. Also, if your team uses Talent SRX speed controllers instead of Victor SP speed controllers, you'll be also using CAN. So how does CAN work? CAN stands for Controller Area Network, and it's a master-slave signal relationship. So there is a CAN controller, there is a CAN transceiver, and there is a CAN CPU. So what happens is the CAN controller will wait and store a message until it's fully delivered, and it will wait to send another message, and it won't send another message until the channel is clear. So the transceiver is what converts the data from the CAN bus levels to another voltage that the CAN controller uses. And then transmitters, in the same way, the transceiver converts data from the CAN controller and changes it to a higher voltage level for CAN bus. So this is normally how the diagram for CAN is wired on the robot. As you can see, CAN goes between the PDP, the PCM, and the roboRIO. Each of the ports are right here. And if you guys are using Talent SRX, again, the Talent SRX, the Talent RX speed controller can be daisy chained with CAN, and then you can end back at the PDP with a terminating resistor. The terminating resistor is there to stop any reflections so you don't get wrong signals. Wait, fast. Okay, so what is I squared C? I squared C is one of the main inputs on the roboRIO. It's not actually commonly used. 1670 doesn't use this. But what I12C is another master-slave relationship. So what happens is that the master communicates with these slaves, and the slaves send back their data depending on the clock. This is normally used for example, like LED drivers, or maybe some gyros use this, which you can attach onto the roboRIO. But again, it's not commonly used in FRC.
So output from the roboRIO, one of them is the DIO, which is digital input output, and it has 3 pins, which you can see there's black, red, and white, and black is ground, red is voltage, and the roboRIO supplies 5 volts, and you would use this to give your sensor, or you're running off of it, power, and then white is signal, and it outputs 3.3 volts or 5 from the roboRIO and to the sensor, so it receives a signal. And so DIO is used with PWM. Well, okay, never mind. So PWM is a way for controlling motors, and so there's cycles of full voltage and ground voltage, and this can be used to produce an analog signal by cycling the full voltage and none really fast. So you can see at the top there's a 50%, so that would be that the motor would receive half of its voltage, and this is Boolean signal because it's either on or off.
Okay, so the SPI with the serial peripheral interface is another bus on the roboRIO that's once again not commonly used. The SPI communicates through one master and several slaves. This relationship is actually very interesting because the slaves can only send information back when the master requests it. So what happens is that there's a clock on the master that goes through each slave and requests information from each specific slave, and the slave can send back information on a different line called master in, slave out. This is master out, slave in, which is when the master sends data to the slaves. Can I go to the next page? Okay, so SPI can actually be wired through 2 different ways. This is in parallel, and this is daisy chain. So these different applications, there are various applications for this. SPI, for example, SPI daisy chain, for example, is mostly commonly used for LED drivers, while this is just for more common applications that are not commonly, once again, not commonly used in FRC, but there are also some gyros which can be used for SPI. So this is a relay. The most common example of relay you'll see in FRC is a spike H-bridge from Vex Robotics. This is another type of speed controller. So this has forward, reverse, and brake. So what happens is the roboRIO sends a signal. This triggers an actual mechanical switch inside the relay, and that just either switches the motor to on, off, or brake. So here's the MXP extension port. So as you guys can see, the roboRIO has plenty of ports, but if you feel like those ports are not enough, you can get an MXP breakout port from Red Robotics. That has more possible ports you can use for your signals, for rope and sensors. This is not very expensive, and there's several boards for different teams. There's Holy Cows has one, 971 has one, which is the Spartan board that we use, and then the Red Robotics also has a ready-made, more simple one. So here, this is just a general replacement of everything on the roboRIO. Ethernet needs to be plugged in, and this is a USB-B type port. That's the port you need to plug into the roboRIO at the beginning to program it. This is the housing for it. This is the power housing. The roboRIO takes power straight from the PDP, and if you lose that housing, you can buy another housing for a very cheap price, so you don't need to replace the entire roboRIO. And this is the RSL port, where you power and give signal to the RSL. Yeah, so I think we're done with this workshop for now, but this is my email. If you have any questions, feel free to email me. I've compiled a list of the sensors 1670 uses, so I can send you that sheet if you need it. Does anyone have any questions?
Thanks for watching our video. Hope you enjoyed it. Don't forget to fruit punch that like button and comment your team number down below. If you want to subscribe, click over here. If you want to watch more fall workshop videos, click over here. I'm from Team 1678, and this is Citrus.